Okay, so we're going to try a new way of recording these, and this is using an app within the iPad itself, so hopefully that alleviates the possibility of using the camera. So one of the BigDog equations that come out of electricity is VER. So these are your voltage. Here's your current. And then you've got your resistance, okay? And your voltage is, oddly enough, in volts. Your current is in amps. Your resistance is in ohms. So to kind of show you a simple example of how this works. So I've got a simple circuit set up, and I've got a voltage of 9 volts. So here's the interesting thing about that. So the voltage is 9 across the light bulb, but if I hook that voltage up across the battery, that's also reading 9 volts. So what that means is that that energy is coming out and then of 9 volts. So it's gaining that electricity, and then it's losing that energy when it comes back down across that bulb. So this will play out large later on. So whatever your voltage is across your battery, if you have a single bulb, that's going to be the voltage across that bulb as well. So we got 9 volts and 1.5 amps. So if we go back to the calculations, and we want to calculate that resistance, so we take that voltage of 9 volts, we divide that by 1.5 amps, we get 5 ohms, okay? So there's a couple of things that you can do depending upon the situation. So in this case, I've got a 5 ohm, so I'm going to go back to that FET simulation, and I'm going to take that, I'm going to increase that voltage up to 10 ohms. So notice that even though I've increased the resistance to 10 ohms, my voltage is still 9 volts, but my current has dropped down to 0.9. So what's important here is that I'm keeping the voltage the same. So if I go to that calculation, now I've got 9 volts. I divide that by 0.9 amps. Oddly enough, I get 10 ohms. So what's happening here is that if I increase the resistance, I have less current flowing through the circuit, okay? So basically that resistance is making it harder and harder to get those electrons through. Therefore, I have less and less charge or coulombs per second flowing through. So here's what's important here, kids. I'm keeping the voltage the same, and I'm increasing the resistance. As I increase the resistance, my current goes down. Now, the other way to look at this equation of VER is that you can also put it in a different situation where we're going to solve for I, and we're going to have I is going to equal 1 over R times voltage. So realistically, in a circuit, what you can typically measure is the current and the voltage, and then you work backwards and you find the resistance. So if you look at this in terms of Y equals mx, so if it's what we call an ohmic resistor, if you do a graph of current on the y-axis and voltage on the x-axis, okay? And I went through and I went back to the FET simulation. And what I did is that, I've already done this, and I'll write down the numbers. What I did is that I kept the resistance of the bulb the same, because you're not really going to change that. Once you get a bulb, hey, that's what you're stuck with. But what you can do is you can increase the voltage. So what I did is I increased the voltage to like 12 volts. I could have added another battery or a bigger battery. Then I bumped it to 15 volts and then up to 18 volts. Okay. Now, a couple of things that you'll notice is that as the voltage is increasing, your current is increasing because you're giving it more energy per coulomb. Therefore, you can get more electrons to flow through this thing. So now if we look at this in terms of a graph, so we had a chart, and here's the data that I collected. Here's my amperage, and here's my voltage, and I had 0.90 and 9 volts and 1.2 amps and 12 volts and 1.5 amps and 15 volts. Okay, now if you come over here and you plot this out, you know, okay, well, there's 9, 12, 15, and then you come over here and you go, okay, well, here's 0.9 amps and 1.2 and 1.5. What you'll see is that this creates this nice sloping line like this. Okay, now if we were to find the slope of this line, a little change in y over change in x-axis, right? So then we're going to have, in this case, 0.9 divided by 9, and picking a couple points, and you get 0.1, which is the slope of the line. Okay, so then, since 1 over resistance is equal to the slope, then the resistance itself would be 10 ohms, voila. So if it's an ohmic resistor, there is a linear relationship between current and voltage. And the reason that we choose that is because realistically, in a physical setup, you're going to keep probably the resistor the same. What you're going to change is the current and the voltage, and as you manipulate that, that's what's going to change, and that's what's going to give you the slope of that line, which is going to get you your resistor. Now, if it's a non-ohmic resistor, then it tends to be like a curved line like this. As your voltage gets, it tends to be like more of a quadratic. So sometimes they'll ask about, hey, on the AP test, is this an ohmic or a non-ohmic resistor? So if it's an ohmic, that just means it's a linear function. If it's a non-ohmic, it's not. Now, the other big equation for today is, speaking of resistance, is that resistance can also equal rho L A. Now, this is your resistivity, and there's a chart in your books, and I don't remember the page number, but there's a chart of different resistivities based upon the material. And you, like copper, your good conductors of electricity have a very, very low resistivity. This is the length of the wire, and this is the cross-sectional area. So obviously, and this number won't change unless you like heat it up, and then that value can change a little bit. It's because as things get warmer, they vibrate more, and so it's harder and harder to get those materials to go through there. So this is your L. So obviously, the longer the wire is, the greater the resistance. So oddly enough, this is one of the advantages of that solar array, that because of the fact that we don't have to push that electricity very far, we don't have very much resistance. Also, your cross-sectional area. So if you want a low resistance, you want a short wire with a big cross-sectional area, because this is analogous to like a hallway. So if you're trying to get a bunch of people down a very narrow hallway, that's going to increase your resistance. If you have a big wide hallway where these people can spread out, so you're dividing by a bigger cross-sectional area, that's going to drop that resistance because the people aren't going to be bumping into each other as much. Now, you can do a little bit of algebraic voodoo with this, and because what you have is R equals rho L divided by A. Now, here's where you can get a little bit clever. If you remember that the volume of like a cylinder, which is basically what a wire is your area times the length. So that would be your cross-sectional area times the length of the wire. So if you solve this thing for area, you get, wait for it, volume divided by length. So if you come in here to this resistance equation and go rho L, and then instead of area, you put volume divided by length, well, then that length flips up here, and you get rho L squared over V. And you end up with the same units. So that's kind of a cool way to do this depending upon what you're given. So here's how this could potentially play out in terms of like kind of an idea with a problem. So let's say that you're told that a wire has a resistance of 0.5 ohms. So what is the new resistance if it is stretched to 3 times its length with the same volume? Okay? So in other words, we're going to take this piece of wire, it has a certain length, right? And we're going to take that wire and we're going to stretch this thing out and we're going to have the same volume. So that's going to be a key part of this. Now, you got to figure, just without doing anything else, that if you're going to keep that same volume and you're going to increase that length, the only way that can happen is if you're going to decrease that radius. So looking at this going, oh, well, if I've got a smaller radius, I've got to figure that when I get done, my answer has to be bigger than 0.5 ohms. So if you just kind of start with an intuitive understanding of what's going to happen, that's going to help you out a lot. So one option is you can start and go, okay, resistance equals rho L over A, right? And we said that that's also rho times length squared over volume, okay? And so that we're going to keep the same volume. So we're going to look at resistance 1 would be rho L squared over volume. And resistance 2 would be rho times 3L squared divided by volume. So if I take resistance 2 and divide that by resistance 1, so I get my resistivity, which is going to be the same. And then I've got 3L squared over volume. And then I've got L squared over volume. So because the volume stay the same, I don't have to worry about that. The resistivity is going to stay the same. So oddly enough, I go up by a factor of 9. So my new resistance then is going to be 9 times greater than 0.5, otherwise known as 4.5 ohms. Now, here's where this actually plays out, because if you, and electrical engineers can take advantage of this. So if they know within a particular circuit, they need like a resistor of a particular ohmage, and they know, and so what they can do is they can take advantage of this and say, okay, well, if I want a very, very specific type of resistor with a certain amount of ohms, I can take advantage of this equation and go, okay, well, that's 4.5 ohms. Okay. So I can take that length of wire, whatever that is, and it's obviously it's based upon that resistivity, and then manipulate that wire to a certain length and cross-sectional area so that you end up with a certain resistance based upon that wire. Okay, kids, that's about it. And so here's what's going to happen. I'm going to scan assignment 22-2, and I'm going to send that out to you. I know you all were used to handing in assignments to me. Don't, okay? This learning opportunity is for you. So I'm going to upload this video onto YouTube, and then I'm also then going to send out to you the assignment. Don't send me the assignment. If you want to do it, which you should, because we're having a quiz over all of this stuff on Friday. So it's very much to your benefit to know this material. But as far as grading it, don't, because it's a monumental task for me to grade and get that stuff back to you, because I've got to scan each page individually and send it back, and it's just horrible. So that's why I'm giving you the assignment. So this learning is very much shifted to your side of the tablet. If you have any questions, feel free to call me. Other than that, hey, stay safe, and I will talk to you all tomorrow.